Today is May 5th. Okay. I will show you some special topics about ink optimization. Okay, so one topic about optimization is multi-objective. So we call this kind of problem multi-objective optimization. So it's so-called the MOO, or MOO problem. And the most common method to solve this is to use this formulation, WIFI, where sum of WI equals 0. So this is called a weighted sum formulation. Okay? So you can minimize multiple objective functions fi at the same time, but they have different importance. But when you sum them up, you need to be very careful. Let's take take some practical example. For demonstration, let's say you want to minimize weight of the product, and it ranges from, for example, 20 to 100 kilograms. Okay, so the unit is kg. And the value is in the range of 20 to 100. At the same time, I would like to minimize, for example, strain in the part under certain load. And you know, strain is having no units. Strain is the unit is like a percentage, right? So the definition of strain is amount of deformation over its original dimension. So it's like a percentage. How much percent of your how much percent deformation was made per geometrical dimension. So it's ranging from 0 to 1. From here you can already see, if you want to put them together, you could be having something like this. Omega 1 times F1 plus omega 2 F2. And here is in the unit of kg, and here is in the unit, no unit, right? But F1 is, the value is in the range of 20 to 100. F2 is a range of 0 to 1. And our weighting coefficient, omega, are so-called the weighting coefficients. They are in the range of 0 to 1. So 0 to 1, 0 to 1. So at the end, overall, this term is in the range of, again, in the range of 0 to 100. The largest value it can be is 100. The smallest value it can be is 0. But this part is 0 to 1. So when you sum them up, the second term plays very small role in the overall objective function. So when you try to do optimization, it's kind of an unbalanced situation. So sometimes, due to the scale and unit difference in each objective function, people try to normalize them before they put them together. So sometimes normalization is good. So why not formulate this in such a way like this? If you normalize in this way, then every factor ranges from 0 to 1. So multiplying a weighting coefficient ranging from 0 to 1, then every term is ranging from 0 to 1. So there you could be having multiple terms, they are all in the range of 0 and 1. So they become equally important. Okay, so this is a normalization. So when you formulate a problem, you need to pay attention to what you have done. Look at your choices. And when you perform some kind of iteration, study the values you get, and try to see the behavior of your iteration. And here is an example of a scaling issue. Okay. So when you are dealing with multi-objective optimization, weighted sum is one way to go. Okay, and there's another issue about MOO, which is which is the selection of the weights. Because you know, if you have a problem like this, and let's say W1 or omega 1 is 0, then this objective function 1 become useless in your entire form. So the term that has smaller value of the weight become less important. Okay, so greater Wi means Fi more important. So lower means less important. But how do you make a decision? So for many times, the selection of the weights basically is based on user preference. Okay? And in this field, sometimes people try to sample different combinations of the weights and try to show people how the objective function value changes with different selections of weights. And if you do that, you may see one interesting behavior like the following. So let's say I've solved a problem like this, and let's say W1 and W2 are already normalized, so they have no scaling issues. And I try to sample the weights like the following: W1 and W2. So I can start from 0, so here is 1, and I increase W1, then my W2 become 0.9, and so on. I try to sample every possible combination, and I solve every combination and get an optimal solution. At the end, you may see something interesting like this, and you can make a drawing. In this particular case, it could be a multi-dimensional problem. So, no matter how many variables you have, but you obviously have two objective functions. So in this particular drawing I'm going to make on the right hand side, it's a two-dimensional figure, and each axis represents each function value. So here is f1, and here is f2. Okay? So this could be a 10-dimensional problem, meaning you can have 10 variables. But now I'm not drawing the figure in the coordinate of x. I'm drawing the figure in the coordinate of each function value. So f1 and f2. And take a usually at the end you will see something like this. Okay. What is this? So there's a name for this. It's called the Pareto front. Pareto front. So who is Pareto? If I tell the name in Chinese, Taiwanese may heard of this name. Pareto is Bolatu. Okay. So, but for foreigners, it's Pareto. Okay. So Pareto front is a person's name. I don't know about the history, but anyway. This frontier is called the Pareto front. What's going on is if you have 0 W1, then only F2 dominates. W2 and F2 dominates. So you will be getting the minimal F2. Okay, so here is F2 equals to 0. Why? Because right here, you are getting the minimum F2, right? But at this particular case, your F1 could be pretty bad. Your F1 value is large. Okay? If you only care about F2 and you choose to have W1 equals to 2, W2 equals to 1, in this case, then you may see this. You may see the right edge of this Pareto front. On the opposite condition, on the other end, if you say W1 is the most important one, so you should be getting the smallest value of F1. So it could be somewhere right here. So this is W1 equals to 1. So you are getting the smallest F1. But in this case, you may not be able to change F2, and your F2 value could be bad. So your F2 could be large. In between, you may see some solution points on the Pareto front. So in this field, in multi-objective optimization field, people sometimes present the entire Pareto front for the user to understand how are the possible solutions for this MOO problem. Actually, every point on the Pareto front is a solution. So all points on Pareto front are optimal. They are all optimal solutions. They are just optimal solutions with different selections of the weights. Okay? So you need to be aware of this. And for engineers, sometimes we don't like multiple solutions. We are looking for one solution, right? So there is one approach, so-called the utopia point approach. So let me explain what is a utopia point approach. So let's say you have a Pareto front like this. This is your Pareto front. And you could have some point right here, and you call this utopia point. Why is this a utopia point? So what is utopia? For Taiwanese, 乌托邦. So where is utopia? It's somewhere like a heaven. It's the greatest place in the world, and you can never be there. Okay. So utopia point means it's a wonderful point, so great that both F1 and F2 are small at the same time, but which cannot be happening. So you can make your decision, okay, where is the utopia point? So there is this utopia point approach. What do? They try to find the closest point to the utopia point from Pareto front. So they use this utopia point approach to make a decision on the Pareto front. So if you really want a single point decision at the end, there are people doing that. Okay? So that's basically the concept of multi-objective optimization. Should be pretty easy, right? So that's I'm not going to write any code. I'm just going to demonstrate. I'm just tell you the concept, and then there are some terminologies in there you may see in the literature. Okay? Any questions? Should be quite easy. Now, I'm going to tell you another, so this is MOO, and I'm going to tell you what is a different kind of problem. It's called a collaborative optimization. CO. Right? So there's a different field of researcher. They work on this CO problem. Why do they do that? They usually work on optimization problems with a very complex and large problem, like designing airplane. let's think about an airplane. Right? So what are possible optimizations in the design of an airplane? You may have the airfoil design problem. You may have seat arrangement problem. You may have flight control problems. You may have structural optimization, and you have power and energy problem, right? You can continue to list out the optimization problems for the entire airplane design. You may even list up to 20 different design problems. You may have aerodynamics problem, right? So for each problem, they may have their design variables. So let's say airfoil design problem, you may have some dimensional problem, and you may have the airfoil problem is very related to the aerodynamics problem, right? So you may have some fluidics parameters. And for the aerodynamics problem, you may have fluidics as well. For the seat arrangement, then you may have some geometrical problem. For control, you may have some engine parameters. And for the structural, you may have a lot of dimensional problems. And also load parameters, right? For energy, you may have the amount of fuels, and also maybe you have power distribution. And from this example, you can already see there are some variables may be related to multiple, if we call these disciplines. There are variables there which are involved in different disciplines. So that's why in this field, sometimes it's called the multidisciplinary design optimization. So we call this MDO problems, multidisciplinary design optimization. MDO. Okay. So CO is one of the approach from MDO. Okay. So if you try to solve the overall optimization in once, sometimes they call this as an all-in-one formulation. Okay. So what is an all-in-one formulation? They may be doing this. They have a huge objective function, usually multi-objective, but they just combine them together. They mainly focus on the constraints. So you may have a lot of variables. Okay? And you will have a lot of constraints, usually. So G1, G2, and let's say Gm. Okay? And each constraint could be representing some function from some discipline. So for example, fluidics. And maybe this is another function from mechanics. And so on. So you will, if you try to put everything together, all the required equations from the physics, from the all the limitations, constraints, just put them together. They call this all-in-one. Can this all-in-one be solved in once? Yes, it can, but there's an issue. Let's think about the reality. Every function right here may be important in different departments of the airplane manufacturer. So maybe there is a department which is working on the dynamics. There's a department which is working on mechanics. So if I'm the boss, so there's a major management office, and we are running this all-in-one formulation. Okay, so let's solve the problem on top in this as a system. Let's run one iteration. Boom. Okay, all the parameters, I got the variables. Good. Now the fluidics department. Let's take a look. Okay, here's what we are going to do for this particular iteration. The main office tell us for this particular parameter we focus on this value, this value, this value. Okay, boom, the values comes to our department. We just make the design modification based on the design variables for that particular department, and then we work on some experiments or simulations so we can evaluate the function performance to get what? To get some of the values of G. And maybe also some feedbacks to the objective function F. Once we're done, okay, feedback to the system, let's move on to the next iteration. But you know, for dynamics, sometimes this operation takes days, weeks to complete one round of analysis. And the other department may be running in a faster pace. So in this particular formulation, sometimes it's not practical, because every department is working in their own pace, own schedule. So it turns out what you can do is you ask them to do your own optimization first. Whenever you're done, send me the optimal parameters. So that's just make some coordination on the top later on. So on paper, in math, this is doable, but in practice, it may not be practical. So that's why people develop so-called the collaborative optimization. So what is a CO? Sometimes they do this. So there are many versions of CO. I'm going to show you one of it. So they call the top as the system level. Okay, and then maybe some constraints, for example, G1 is right here at the bottom. Okay, and so maybe here x1 is here, and maybe x1 or x2. Okay, so we call this a subproblem number 1. Okay, so it's like a discipline number 1. Okay, so what would be the objective function? So over here there are people doing this. They are trying to minimize, let's say, x1 minus x1 from the system plus x2 from the system. So system is gonna assign some like a target value for the subsystem. So over here, they assign target values like this. So you will be, so the target value may not be satisfying the constraint for this local discipline. But locally, when you solve subproblem 1, you will try to find the variable value x1 and x2 as close to the target value as possible. But meanwhile, satisfying your local constraint. That's the idea. Once you're done, you will return your local optimal. So we call this x1 sub and x2 sub. Okay? So on the top, in the system, what do? You will try to make sure actually, no. I think they, let me think about it. Oh, no, this is not what they do. They get back the sub, but I need to draw another sub. For example, there is a subproblem number 2. And let's say for sub number 2, maybe there's a G2, but this time there's an x1 and x2. Maybe the x1 is related to discipline number 2. So I'm gonna draw this in this way. So over here you can see the system assign x1 sys and x3 sys, and when you return the value, you will send x1 sub and x3 sub. But over here you can see you will have x1 sub from the left system, also x1 sub from the right system. So they could be different value. So I can call this sub 1, and I call this sub 2. So the issue is when you are handling the local optimization problems separately in each discipline, they may not coordinate well. They don't know what's going on in the other system. So we sometimes call these the shared variables. So if there's a whenever there are more than two disciplines that are sharing the same variables, so the coordination of the shared variables is important. So on the system level, they need to do some coordination of the shared variables. So what they did is they will try to say x1 minus x1 sub 1, x1 minus x1 sub 2, they wish this equals to 0, but it's impossible because sub 1 and the response of sub 1 and sub 2 may be different. So there are two different points. So if you want, at the system level, when you try to find a point that is close to the solution from sub 1, also close to the solution to sub 2, at the same time, how is it possible? So sometimes they try to make this smaller to some small value. So at the end, usually, you will get the middle point between x1 sub 1 and x2 sub 2. Okay, so the purpose of doing this kind of constraint is to do some coordination. And the coordination of the shared variables is actually the most troublesome part of MVO. Okay? So in NTU, there's a Professor Zhang Kuiyuan. Professor Kuiyuan Zhang from NTU. His dissertation is about MDO. So if you are interested in MDO in the future, you can go find his dissertation. They developed some method called the ATC. What is ATC? Target cascade. What is A? Artificial? Remember the method is called ATC, and T is target, and this is cascading. What is A? It has been a while, it has been 20 years. I forget what is A. ATC. Let me. analytical target cascade. Okay, so that was his in his research group. They have been using ATC. So what's the difference between ATC and CO? CO mainly focus on two-level structure, one system level and multiple subproblems. So if you have 100 different disciplines, in the second level you will have 100 subproblems, but only one system. So what does ATC do? ATC try to make multi-layer structure, so they call the hierarchical structure. Okay, so it's like this, a big system level, and they have, for example, sub 1 right here, and they have, for example, sub 2, and they try to have lower levels. So you can call this a sub 1-1, and this could be sub 1-2. So it forms some kind of hierarchical structure. Okay? And in each particular subsystem, what's going on? So I will try to show you in one of the subsystem. You may be minimizing the difference between local variables and target variables. So basically on the top system will assign target variables. Okay? And meanwhile, in your constraint, you will have your local constraints. And also, it really depends on the version of your format. Do you want to put the coordination of lower level variables in your object function or in your constraint? It depends. So meanwhile, some people try to do this. They also put it in the object function. So the difference between local variables and the response variables. So the lower level will feedback some response variables. And you will send some response variables to the top for this particular problem. And also, you need to send some target variables to the bottom. So it becomes some kind of hierarchical structure with value passing between each system. So at certain level, you are receiving assignments from the top, and you are also assigning some target values to the bottom, and you are getting some feedback from the bottom, and after some analysis, you send some feedbacks to the top. So it's like the top level is your advisor, middle level is like a PhD student, lower level is like a master student. Your boss will just say, okay, do this. You do something, you assign another target to the bottom, so all the feedback cascade transfer back level by level, just like that. So it's a different way of handling multiple disciplines, but you really need to make a decision of how this whole system is being separated in multiple chunks. And you need to design your own way of variable passing. Okay? So that was another approach for MDO. Okay. So I have finished 2 different topics today. Any questions? Any questions? Okay. So I have another topic I would like to share with you. It's called the optimization with uncertainties. Okay. So what kind of problem is this? Whenever your problem has random variables and there are so-called the success rate and failure rate, then your problem is not easy to handle. So what do you mean by that? So on the opposite of optimization with uncertainties, you are dealing with optimizations without uncertainties. So without uncertainties, we call this kind of problem as a deterministic optimization. Okay? So what is a deterministic optimization? So it's like this. Minimize subject to g of x. So x deterministic. So whenever you say, oh, this is your optimal, it's your optimal. There is no uncertainty, no errors, precise, deterministic. Okay? But when you have with uncertainties, there's an issue. So usually it's a probabilistic optimization. So how does it look like? Usually it's like this. You cannot control, so you will have random variables, but you can only control maybe the mean value. So I'm gonna say mu x, right? It could be a vector, mu x. I will tell you what is mu x. And you will have probability. So probability of g, and pay attention to this. Right here you have a capitalized x. And now it's larger than. And here is smaller than again. So what's going on? Why are you rewriting so many things? So I have to define something. So where x is a random variable And for many times, for many cases, it's normally distributed. So here I can write in this way. For simplicity, I think I will erase the vector sign, otherwise it's so complicated. So I will just focus on single variant derivation. Just say single variable, because with uncertainties already very complex. Okay, so this is what is n? N means normal distribution. Right? Mu is like the mean, and sigma is the standard deviation. So it's like x is like a mean value plus or minus sigma x, something like that. Okay, so in your objective function, you are only controlling the mean value. You want the average of this uncertainty to be controlled. You are changing, and what's the distribution? Distribution is a whole chunk of probable solutions. So if you take a look at the one-dimensional coordinate, maybe this position is the mean, and here is what's your vertical axis right here? This is probability density, basically. So this is called a probability density. Okay. So this is like a standard deviation. So it's like you're moving the mean. The whole chunk of the normal distribution moves with you. Okay? And what's going on with the constraint? This is the probability. And this is called the allowable failure rate. Okay? And what is this? Take a look at the original problem. This is the safe event. When we are having smaller than or equals to 0, it's a good design, safe design, right? But when we are on the opposite side, when the g function value is larger than 0, this is basically the failed event. So this whole thing is failure probability. So basically, you are minimizing the function value with respect to the mean of the distribution, subject to the failure probability has to be smaller than the allowable value. This is a completely new formulation compared with deterministic optimization. So in probabilistic optimization, you are handling a much more complex kind of problem. Okay. So in Taiwan, let me see how many professors are working on this. I know Zhang Kuiyuan knows about this. I know some civil engineering professors knows about this kind of problem. Not so many. I am one of them. So maybe 5 to 10 professors knows this kind of problem. But I believe this kind of problem is the formulation to make reality and the theory closer. Because you can say deterministic optimization is a theoretical solution, but it doesn't handle uncertainty. Okay? So let me show you one example, just mathematically. Why the deterministic optimization may fail. So let's say we are handling just 1D problem. So just 1 is subject to, let's say, and we don't need a 1. Larger than. Okay? So to make a drawing, this is x, and here is 0. So this is f equals to x squared. Okay, and here is 3. So obviously, the solution is right here. Right? For deterministic optimization, this is where your solution is. But if you are handling the problem in a different way, let's say x now is a random variable. So the only difference between the original one and the new one is it has some kind of uncertainty, normally distributed, and the mean value is like this. I will just say the standard deviation is a value of 1, something like this. So right at the optimal solution, if I make a drawing of the random distribution, it will look like this. Here is 1, right? Here's 1. Here's another 1. So if I use this vertical axis and use it for the probability density as well, the probability density will look like this. Okay, so it's like right here. This is sigma, right? Because this is the 3 is the deterministic optimal solution. But if, as a manufacturer, when you produce something in a dimension of 3, and if the manufacturing process has some kind of uncertainty, let's say the standard deviation is 1, so you can only say your value is, your random value is like 3 plus or minus 1, like this. You can only say that, right? And let's take a look at the failure rate. So over here, if you pay attention to everywhere that is within this blue area. Okay. So everything within the blue area, the light blue area. Can anyone tell me what's the percentage of the light blue area? Probability of the light blue area. If the whole distribution is 100%, then half of it is half of 100%. So 50%. So there is 50% of chances that what's going to happen? X violates the constraint. So what does that mean? That means the failure rate is 50%. So in your deterministic design, if you move your design point to the optimal, you solve your optimization problem right here. And the optimal solution is 3. If there's no uncertainty, that's great. However, if the uncertainty exists, then 50% of your design is going to fail in this particular example. Okay, so it's very bad, right? Can we control the position of mu x so that I can control the failure rate? So the problem is, how do I control failure rate? How can I minimize mu x squared subject to probability? Here is random x smaller than 3, and I want to say 1%. If I do this, then what is the optimal solution? You can only try by trying, right? So now I'm going to show you how to handle this kind of issue. So if you take a look at the okay, we are going to convert this problem into a so-called standard normal space. So here is original space. Here is x, and here is mu x. Here is just a probability density. Okay, and okay, we are going to convert this into a different space. This space is having a small case u, and right here it's gonna look like this, and the standard deviation is 1. The mean value is 0. So this guy is called the normally distributed x. But after the transformation, it becomes a capitalized U. It's a standard normal distribution. So how do we make this transformation happen? U equals to x minus the mean value divided by standard deviation. So this is how you can convert the original space to a standard normal space. So this is like a original design variable, and this is the standard normal variable. Okay, so the whole distribution is being transformed into a new space. It's called the standard normal space. Okay, so let's try that. Why do we do that? Because we want to evaluate failure rate. So let's try to do this. X smaller than 3, right? So over here, I can rewrite this equation as follows. X equals to mu x plus u times sigma x, right? If every point inside the x space can be converted to the u space by this equation, then the whole chunk of the distribution can be transformed to the whole chunk on the right-hand side in the same way. So the entire capitalized distribution, the capitalized symbol represents the whole distribution. Satisfy this equation as well. Okay, so I can rewrite the equation in such a way. Mu x plus u sigma. What is my sigma right now? My sigma right now is 1, right? So times 1. Small. And what is my mean value right now? My mean value right now is 3. So my mean value is 3. So this is my mu, this is my sigma x. Okay? Okay, so let's derive this probability of, so it's gonna be u smaller than 0. So it's like you are studying the standard normal distribution on the right hand side, and you are studying the percentage of this distribution being values smaller than 0. So did you notice that originally we are handling the original space with a mean value of 3, standard deviation of, in this particular case, also 1. But after normal distribution transformation, I convert everything into the normal standard normal space, and we are now handling this standard normal coordinate. And this particular standard normal distribution can be computed actually. So in MATLAB, it's I think it's a norm. Let's say this is MATLAB code. If you say norm CDF, it gives you this value. Yes. But now we are not in MATLAB. What can we do as well? Let me show you in internet. So I need to hook up to internet first. So just type in standard normal distribution table. Okay, there's a table. Maybe this one. Okay. So open the table. Here, it's telling you in the standard normal distribution, and what does this table mean? If you try to compute the area percentage underneath this dome shape, it already computes everything for you in the table. And this particular case, it's showing a red area from negative infinity to 1. So this is showing you probability of standard normal distribution smaller than 1. So basically capitalize U smaller than 1. So what's the percentage? Over here, if the whole chunk is 100%, so this should give me a value like 60 or 70%, right? So let's read this table. So we are reading the position of 1. So right here. For the left column, 1.0. And first row gives you the second digit after the dot. So basically you read 1.0 right here on the first column, and then you read 0.00 from the first row. So at the end you get this number, 0.8413. Did you guys see it? 0.8413. That means this red area is 84.13%. Okay? So I will take us. So from here, you can check the normal distribution table. There are many of them on the internet. Usually it looks like this. Here is 0, and this is like a U, and you can say this is like a UA, and the area can be computed as a percentage of, if this whole thing is capitalized U, smaller than UA equals to the integral of negative infinity to UA, and the function here, I think people try to use this function, and UD. Okay, so what is this phi function, or phi? So basically, this is called the probability density function, the PDF. So basically, if you want to describe this dome shape mathematically, this is the PDF. Okay? And people also say the value, the area value right here, they also name this as the capitalized phi or phi, and put a UA here. So this function is called the cumulative distribution function. So it's the CDF. So that's why in MATLAB, it's called a norm CDF. Because if you try to compute the area from negative infinity to certain point, the total value is cumulative distribution function. So in MATLAB, norm CDF means you are computing CDF of a standard normal distribution, having a integral from negative infinity to certain point. And the input for MATLAB right now is 0 on the top, but actually it's the position of UA. Okay, and in normal distribution table, usually it looks like this. Here is they usually do this. And here is like this. Right? So if you are handling, if you are trying to get a value right here, what does that mean? That means this is the value of P, probability of U smaller than 1.11. If you are focusing on a value right there. And you will realize in most of the normal distribution table, there's no negative value. But in the drawing on the top, there's actually negative ones. So how do you handle negative values? What you can do is, let's say, you want to know if I'm handling a probability from negative infinity to negative 2. How do I do that? So you can, it's gonna be 100% minus U. So basically 1 minus why is that? Because this standard normal distribution function is symmetric about the 0 axis. So you can compute, so right here, I can show you by some graphics. We're trying to compute, here is 0, here is negative 2. We try to compute this, right? You want to know the percentage. But if you flip it, here is 1, here is 2. If you compute this whole thing, because only the positive UA can be found in standard normal table. So you compute P of U smaller than 2 and use 1 minus that value, then you got the answer. Okay? So, I can tell you, so let's figure out how to get what we want. How do we get 1% of our safety allowable failure rate? 1%. So let's take a look at 1%. 1% means I need the failure rate to be 90%. So from this table, I will try to find a value that is the closest to 90%. 90, oh, here's one. 0.8997. It's very close. 0.8997. So 0.8997, that is gonna be, let me attempt this. 1.28. 1.28 gives me 90% here. This particular one. 0.8997, right? So from the Why am I doing this? Let me tell you again. So from the standard normal distribution table, I found a spot. It gives me A997. Okay. A997. No. I should pick up a greater one. So maybe 9015. Better. 9015. So I will pick up 9015. Okay. But I will tell you why. 9015 on the top it's a 0.09. So here is 0.09. Okay. On the left is let me see, 9015. Right? So it's 1.2. Here is 1.2. From the table, I read this. What does this mean? This means probability of U smaller than 1.29 equals to 0.9015. Okay? So what I can do is, it tells me something very importantly. Equals to, so this would be 0.985. Why? Let's draw a figure. So this is telling us, here is 0, here is 1.29. This area is 9015. So if I flip it like this, and here is negative 1.29, and the tail on the left is going to be what? 1 minus 0.9015. So this is going to be a very small value. This is what I'm looking for. Because in my design, I wish my design point have a left tail that is only having a failure rate of 1%. So I should move my design point toward right so that this light blue tail becomes smaller and smaller until that small left tail is only 1%. Just like this particular case. So now, reversely, I check the normal distribution table I found. In the standard normal distribution space, if I have U smaller than negative 1.29, the percentage of the left tail is only 9.85%. No, then it's not good. It's not 1%. Sorry. So I picked up the wrong one. Yeah. So 1 minus. Yeah, so this is not a good choice because I should pick a value which is 0.99. So at the end, the left tail is 1%. So I pick up the wrong value, not this particular one. So let's do it again. I should find 0.99. Where's 0.99? Okay. And I should find 0.99 and slightly larger. So there is a point. Okay, this is perfect. 0.9901. Did you see it? 0.9901. This is perfect. This is how I can get only 1% of failure rate. So this is actually success rate for me. 99.01 success rate. So 0.99. So that was a poor demonstration. This is bad. This is wrong. Okay. Let me do the right thing again. So I found Spot is having 9901, which is perfect. And I need to read what's the value at the left, the left column and the top row. So from here, the 9901 right there. So it's a 2.3 on the left, 2.3 right here. And oops, 9901. 2.3. 9901. Okay, this one. So 0.03. 0.03. Okay, so what does that mean again? This means the probability of standard normal variable smaller than 2.33 equals to 0.9901. So, which implies u smaller than negative 2.33 equals to 1 minus 0.9901, which is 0.0099. That is 0.99%, right? Which is good because this is smaller than 1. I was looking for 1%. So if I have, now I want to convert this u back to my original space. So earlier I had x u equals to x minus mu x over sigma x, right? So how about capitalize U? It will satisfy this. It will be like this. Okay, so I just plug it in. Plug in. So I will plug it in such a way, x remains x, minus, but this time mu, I keep it unknown, okay? And then, what is my sigma? My sigma is 1. And smaller than this, right? Hold on. Why? Do I pick out a value? Hold on. Pick up a value. Let me see. Okay, I think that works. That works. Yeah. So I will be sure if I do this, my failure rate would be 0.99%, and it is smaller than my desired 1%. it will satisfy what I'm looking for. Okay, so if I if I let me see how I should. So if I do this, x let me see what I should do. Mu x minus 2.33. Is this the right way to get? No, I don't think this is the right way. So I should. Let me see what I should do to get the right. This is not the right way to do it. So I should start from here. Okay. That doesn't gives me a good way to get where I should locate my mean value. So not yet. So I think I should derive in this way. So x smaller than some. This is 3. This right now is okay. Smaller than here, right? Let me see how I can derive it. If I apply u here minus ux right, this is all right, and then I can do this. U smaller than mu x plus 3 sigma, right? This is okay, and then I can convert. This is 1%, right? This is 1%. So I now convert I will convert because this UA equals to P UA right? So if so from here UA equals to the inverse of the CDF, I will have this, right? So I will apply, do I do that? Inverse of CDF. Oh, yes. If I do that, I will get UA, right? So mu x plus 3 sigma x. After applying this, smaller than 1%. So this is close to, we already know, negative right here. See? Negative 2. So recall, it's a little difficult. U smaller than negative 2.33 is close to 1%, right? If I apply the inverse of this guy, it's a little difficult. So it's like this. It gives me negative 233. So this is negative 233. So over here, this is 1. This is unknown. But from here, I get mu x plus 3 times 1 smaller than 2.33. So mu x has to be something's wrong. I know something's wrong. Negative sign. I always forget about the negative sign. Negative sign is, let me see where. Smaller than this. 1%. 1% is on the right hand side. I need to apply a negative sign. The most difficult part is this negative sign. Here is a 3. This one is right. When you define this standard normal space on the left hand side, 1% on the left hand side. But when you do the conversion, it's a negative value. So whenever you apply this, it's a, which one is a negative value? This guy. This guy has to be positive because when you do this conversion, everything is negative. It's like a multiplying negative value. So this has to be greater than. So because everything is negative. So greater than this. So this one is greater than. So it will become negative 3. Still incorrect. Greater than and also changing the sign. I better derive in the right way. This is, in this case, U is negative. Yeah. So this is a negative value. Okay? So when we apply inverse CDF, we get this. Do we still have the same sign? I should make it larger than 2.3. After conversion, this space on the left. If it's on the right, it's easier, but now it's on the left. That's why everything is negative. Everything is negative. Smaller than. Probability of. So this is a negative value. This is a negative value. You. Mu, I know mu on the right. It's actually positive. Event of x. I know x should be on the right. X should be larger than 3. So this value, this chunk must be larger than 3. That chunk larger than 3. Probability. Standard normal space. The cutting point. So the ideally I'm looking for in the U space. This is U0, and then here is 2.33. negative 2.33. And so this is 1%. I wish I can convert this back. So UA equals to negative 2.33. If I convert back, what is the mean value? So mean value so the distance using distance is a very dangerous way. You know, it's my PhD work. It has been 20 years trying to recall this. So in the original space, it's gonna be like this. Here is x equals to 3. Okay, and this should be a good mu x. Okay, so that here is 1%. So I'm looking for this mu x. So at this particular mu x, probability of this x smaller than 3 now equals to 1%, right? And if I convert, x can be rewritten as u equals to x minus mu x over sigma x. So this is this. Okay, so x can be rewritten as mu x plus u times sigma 1 smaller than 3 equals to 1%. And if I convert this whole thing by inverse of this. So here I can rewrite as u smaller than 3 minus mu x equals to inverse of 1%. And then this conversion is negative 2.33 already. This should be 3 minus mu x. So mu x equals to 3 plus 2.33. Finally. So mu x equals to 5.33. That's the solution. I don't know what happened earlier. Okay. Forget about what I did. Sorry. This one is better. This is a much easier. I'm sorry about. Forget about this. Very sorry. Yeah. So think about it. In the standard normal space on the right hand side, I want to keep a distance of negative 2.33, so this left tail become 1%. So from the standard normal table I found, if this integral point is negative 2.33, I'm sure the left tail, this is called the left tail of this distribution is 1%. So if I convert back to the original problem, I want to move my mean value from 3 toward right. So the left tail becomes smaller and reach 1%. The original optimal solution is right here. This is the original one. My optimal is right at 3, which is not safe. I should move the mean value toward right. But I don't know how far away I should move. So based on this standard normal distribution, I realize I can, in the U space, when this cutting point right here is negative 2.33, I know the left tail is 1%. So how about the original space? And from here, let's say right at the 1% case, for the left-hand side, probability of random distribution x smaller than 3 equals to 1%, exactly 1%. I can convert to P of mu plus capitalized U times standard deviation 1 smaller than 3. I want this to be exactly 1%. But I don't know my mu x yet. So here I will perform this inverse CDF transformation. So let me remind you what's happening here. I actually wrote it here. I wrote it. This is not wrong. It's just not something like, it's not wrong. Let me copy this. So if you try to understand what's going on here, let me paste it. Erase this. So from here, this is this. Okay? So UA, right? So the CD, this is the so-called the CDF, cumulative distribution function, basically equals to probability of capitalized U smaller than UA. And if you apply inverse of this function, you will get UA. And this is the right hand side. Okay? So I did that. Here you can rewrite this whole thing as U smaller than 3 minus mu x, right? Basically this. So I apply this inverse CDF. This is like a inverse of CDF. When you do that, you can get UA. This is basically UA. But on the right hand side, inverse of 1% is negative 2.33. Okay, because CDF of negative 2.33 equals to 1%. So the right hand side becomes negative 2.33. And from this equation, we found, mu x has to be 5.33, so the failure rate stays 1%. So this kind of optimization is called reliability-based design optimization. So-called the RBDO. Okay. I'm sorry, I didn't know why right here I couldn't rewrite what I want, but here is what I'm looking for. Okay. So it's a way, actually, this is a way to find the so-called the safety factor. People often call this safety factor because from the original design, let me show you. This is the original design. Okay, this is the original. Okay, and your design was here, and the failure rate was 50%. And now, if you move on, here is x equals to 3. If you move on to x equals to 5.3, if you move right, and your distribution becomes like this, and the distribution right here is only 1%. So the failure rate now greatly reduced to 1%. Okay? And people sometimes call this idea like a safety factor. So it's like you provide safety factor to the entire design. But how do you compute so-called the safety factor? Over here, if you use a concept in solid mechanics, it doesn't help you, because the safety factor usually is some limit over a safety factor. But because our failure condition is on the left hand side, there is a inverse concept compared with solid mechanics. So this is similar. This is like similar to applying safety factor. Okay? But in our field, we don't usually call safety factor. We call reliability index. So where is reliability index? This is reliability index. So it's usually defined as beta, and in this case, it's like CDF of negative beta in our case. So this 2.33 means something. Right here, this distance is reliability index. This distance, beta. But in our particular example, it's on the negative side. So this is becoming negative beta, because a beta is a distance. Okay. Okay, so here's the final portion of my demonstration today. Let me go over again what has been covered today. Someone's calling. Today we talk about multi-objective. So key terminology includes this weighted sum formulation. And if you have scaling issues, you can do normalization. And so there could be multiple solutions on the Pareto front. And there are people using this utopia point approach to find a single optimal on the Pareto front. But all solutions on the Pareto front are optimal solutions based on different user preference of the weighting coefficient. And we also talk about this MDO, multidisciplinary design optimization, to avoid, if in reality you cannot do this all in one formulation, people try to separate this problem into multiple smaller problems. One approach is called the CO, collaborative optimization, CO. So basically, they separate this big chunk of problem into smaller ones. There's a system level, there are subsystem level. Okay, and they have this sharing variables. Okay, and certain group of researchers, they also focus on this target cascading, analytical target cascading, where they separate the whole chunk into multiple layers to form this hierarchy. And in each structure, they have their local constraints. They try to minimize the difference between the local variables and the target values, and also minimize the difference between the local variables and the response values. Okay. They also assign values to the lower level, respond values back to the upper level. Okay. And finally, we talk about optimization with uncertainty. So what is uncertainty? Basically, not deterministic. It's gonna be probabilistic. Okay? So in probabilistic optimization, you are going to have a control point, usually the mean value, and the failure rate must be smaller than the allowable level. Usually this allowable failure rate is small, like 1%, 5%, but how do you control it? How do you precise choose your variables so that you find the best design you can, meanwhile controlling your failure rate. Okay, so usually we are handling normal distributions. That means the uncertain distribution has a mean and also standard deviation. And in this particular example, you realize we had this transformation to the standard normal distribution. Okay, from the normal distribution to standard normal distribution, using this particular transform. And we realize that the normal distribution can be described as a probabilistic density function. And if you do the integral of it from negative infinity to a certain point, and the area underneath the distribution is basically the probability of that certain side. So it's called the cumulative distributed function, CDF. Okay, and you can find percentage, basically CDF values from the normal distribution table, like I showed you earlier. And because normal distribution is symmetric from left to right, you can use this flipping trick to compute which side of the area you're computing. And in our particular case, I'm looking for this tail distribution 1%. So I found if my UA point is negative 2.33, my tail percentage is almost 1%. Okay, so that's why I'm trying to use it to find the proper position of my mean value of the original distribution. Not working. Yeah, so come to here. In the standard normal design space, I want to keep a distance of reliability index from the origin to this UA point. And the distance is going to be 2.33, and because it's on the negative side, so this UA point is going to be negative beta, negative 2.3, so that the left tail is 1%. So how about converting this back to the original space? I'm looking for this new mean position so that this tail percentage remains 1%. So this is where you can just plug in certain values, and then you realize finally if you position your mu at 5.33, like this particular drawing, if you on the right, if I draw the objective function, this is x equals to 0. Our objective function was minimizing x squared. So our objective function looks like this, right? This is minimizing x squared. So which means our optimal solution is right here. I want to keep the mean value of the random variable at 5.33. Because of the random behavior, there is only 1% of probability that my uncertain variable is gonna violate the constraint. So this is failure rate, and it's gonna be probability of my uncertain distribution where the mean is located at 5.33. This uncertain distribution, the whole thing, smaller than 3 is gonna be my fail event. Now is being controlled as 1%. So if I shift my design point right to 5.33, I give myself a safe margin. The concept is just like a safety factor, but it's precisely determined. I need to move right to 5.3. Okay, so that's basically RBDO. Okay, so yeah, sorry about poor derivation process today, but that's been 20 years. I need to sometimes recall some part of my brain, and then derive this. In the past, let me see, I started my career in 2012. Now it's 2025. So in the past 13 years, I taught How many graduate students? Maybe more than 50, definitely. How many you work on RBDO? Only one. I have one master student who work on RBDO. Only one. So it's not easy. But from this topic, you can realize there's a lot of mathematics, statistics, and it's very practical actually. So there's already commercial software which can work on RBDO, but probably you guys have no idea what it's about and where. I know for vehicle companies such as Ford or aerospace companies such as Boeing, they are all using RBDO. Okay, so when I was a PhD student, I worked with many, in this RBDO society, there are many professors. There are also many researchers in the USA manufacturing company. They have design group who works on RBDO because they cannot allow the failure rate to be greater than the limit, because it's about human life. Drive your car, the aerospace vehicle, and also for military devices. Nowadays, the manufacturer, they cares about this reliability. So really is something we should work on in Taiwan. I mean, someone should work on it. So I hope today's introduction about RBDO inspire you somewhere. Some of you may be inspired. And if you really want to work on reliability, definitely you can let me know in the future, because at least in our department, in our school, probably I'm the only one who's working on RBDO. The other professors in RBDO field is in the civil engineering. I know I'm not sure if the previous chairman is Professor Yang Yidong is also working on RBDO. There's another one, I think is Professor Liao, I think. He transferred to NTU. So there are some professors in Tech and also NTU who works in RBDO, but not too many. So if you are, or if in your research you need to know about uncertainty or reliability, you need help, you can let me know. Okay, so that's it for today. I didn't record myself, so only that. I didn't record my screen. Anyway, so do the attendance check.
Okay.
So otherwise, no attendance is scored. Today is Ben is here. 万中 Kelvin Tron the Vietnamese. No, he's not here. Jerry's 右滑。哦， 艳红。Jump, is it jump? 红。哦 ，OK。Roti, roti, roti. Not here. Jason. Jason. 君泽 Jason。君泽不是？君泽。你是君泽啊？对。哦，好。OK。博鲁。玉成。Sam。圣兵。Here. Okay. Ray. And 思乔。阿兹米奇。义成。范平。David. Warehouse Wilson. 佑嘉。Who missed the call? Everyone is here? Okay. So the missing one is Tron Lei and Rati, right? Okay. Okay. See you guys. I think the next week. Oh, next week is progress report. Are you guys okay? Progress report. You don't need to write anything. Just present the progress. Do you need another week for progress? Okay, so let's switch the progress report to May 19th.